Hi, and thank you for your interest in expert geophysics and MobileMT. During this presentation, the technical developments of expert geophysics will be discussed, as well as the application of these developed technologies through various case studies, in order to highlight how technical limitations of existing airborne EM systems have been overcome to provide high-quality data and meet client objectives. Mobile magnetotellurics, commonly known as MobileMT, is a new approach to the acquisition of electromagnetic data that involves an airborne bird, towed by a helicopter, that measures variations of the magnetic field with 3 orthogonal induction coils, while a ground station measures variations in the electric field in 2 directions. This technology pushes the limits of existing airborne EM systems in terms of sensitivity, resolution, and investigative depth range. The method has proven to be capable of showing detailed subsurface conductivity structure. MobileMT allows for identification of geologic structures, alteration halos, contrasting lithologies, and even certain types of mineralization from near surface to deeper than 1 kilometer. The data can be used to define porphyry targets, as well as volcanogenic massive sulfide deposits and kimberlite pipes. When compared with other popular airborne time domain EM methods, MobileMT does not have issues detecting differentiations in highly resistive ranges as well as superconductive targets. It also is not impacted by parasitic phenomena like induced polarization and superparamagnetic effects, which destroy inductive response or create pseudoanomalies. And it always outperforms methods with control field sources in terms of depth of investigation. Topics that will be discussed during this presentation include a brief description of the main principles used in the airborne EM sector and a comparison of their relative depths of investigation and other features to provide an assessment of the capabilities and limitations of each method. Then, a review of the source of energy used by the MobileMT system, as well as the fundamentals of data acquisition and data processing. A discussion of the exploration advantages of the MobileMT system will be provided, as well as a description of how the technical solutions that went into developing this technology were able to overcome limitations experienced by other systems and principles. Some examples of acquired data will be provided in different geoelectrical conditions acquired in different types of terrain. A direct comparison of data acquired using other airborne EM systems will also be shown. And finally, the current state with regards to technology and experience of the MobileMT airborne EM technology will be evaluated. As a reminder, the premise of all EM methods is induction. There is a primary field which induces a secondary field, or response, that is dependent upon the geologic environment. In the VLF method, the primary field is created by distant radio stations. In frequency and time domain methods, the primary field transmitters are included into the systems in the form of loops or coils. For magnetovariational and audio magnetotelluric methods, passive or natural fields generated by atmospheric phenomena like thunderstorms and lightning are the primary field source. The wavelength of the primary field is a determining factor regarding the depth of investigation of the method. Airborne EM methods have been in practice for approximately 70 years. As mentioned previously, the airborne EM methods differ in terms of their primary field source and consequently in their depth of investigation. The shown depths of investigation in the table are approximate because the actual depth of investigation will depend on how conductive the environment is and on technical features of each system configuration, but the ratio of the depths between methods is quite close to reality. Some examples of frequency domain systems include F400 and H400 from the 60s and 70s, as well as the DIG-HEM system, which has been used for several decades. Geotech introduced the Hummingbird system in the 90s, and in the same decade, AeroQuest introduced the Impulse HEM system. The main concern with frequency domain systems is limited depth of investigation. The true revolution in airborne EM technologies came with the advent of time domain helicopter systems in the 2000s. Examples of these systems include AeroTEM, NUTEM, HeliTEM, VTEM, SkyTEM, and many others. Generally, these systems perform better than frequency domain systems as they are spatially highly focused and the depth of investigation is comparatively better, but still very limited in conductive environments and in the presence of conductive overburden. Other problems of time domain systems are related to the inability to detect superconductors and difficulties with differentiation in the highly resistive range. Under certain conditions, the time domain method suffers from such phenomena as induced polarization and superparamagnetic effects, which destroy useful inductive signal or create pseudo-anomalies. In the case of both time and frequency domain EM systems, as they both make use of controlled source primary field transmitters, the efficacy of both depends critically on flying height. The MobileMT technology exploits the principles of magnetotellurics. When compared to time and frequency domain methods, the principles of magnetotellurics provide the greatest depth of investigation and are sensitive to a wide range of resistivity values. The audio magnetotelluric principle has long been used in ground geophysics. The first airborne magnetovariational system, called AFMAG, was announced in 1958 by Dr. Ward, but the system suffered limitations due to electronics and the analog handling of data. In the early 2000s, Dr. Peter Kuzmin at Geotech started to develop modern versions of systems based on the AFMAG principle. In 2018, Expert Geophysics Limited introduced the latest and most advanced generation of passive airborne AFMAG EM technology, MobileMT. Designed by Dr. Peter Kuzmin, MobileMT combines the latest advances in electronics, airborne system design, and sophisticated signal processing techniques. In contrast to other airborne EM systems, MobileMT technology uses natural EM fields to investigate the electrical conductivity structure in the subsurface. The system does not use any artificially driven generator or transmitter, which firstly creates noise and secondly is very limited by energy in airborne modifications. Lightning events and thunderstorm activity that occur worldwide cause natural variations in the Earth's magnetic field, including electric or telluric currents. The natural phenomena create strong EM source signals over the frequency band which the MobileMT system acquires measurements over. In other words, over the audio frequency range. The MobileMT base station records horizontal component electric field data. An example of historical levels of signal measured at the base station, monitored throughout the day, is provided here. Below is the typical signal spectrum for each frequency channel in the full range of frequencies measured by the MobileMT system. The airborne MT technology shares many similarities with the ground MT method, but there are some differences. The measurement system consists of two main parts. The first is a stationary base station that measures horizontal components of the electric field. The base station consists of independent signal and reference channel, which aids in providing bias-free data. The data from the base station is monitored through the entire survey using a satellite. The second part is the three-component towed bird receiver that measures variations in the magnetic field at 74 kHz to produce a time series dataset that ensures high-quality data synchronization and processing. The system is connected to a data acquisition unit located inside the cockpit of the helicopter. Fourier techniques are applied to the merged base station and airborne recordings to calculate 6 admittance matrices in different frequency bands and for different time windows. Through modular computation of matrix determinants, which are rotation invariant parameters, the apparent conductivity for each frequency window is calculated as the main output parameter of MobileMT mapping. The specific technical advancements that enable exploration advantages include measurement of magnetic field variations in 3D. This provides sensitivity to any direction of geoelectrical boundary from horizontal to vertical. The measurements are obtained over 4 decades of frequency, from 26 Hz to 21 kHz. This allows imaging of both near-surface structures as well as those at greater than 1 km depth. The frequency range is divided into 30 windows that provide high in-depth resolution and a good opportunity for data selection. The very high sampling rate of the airborne data as well as the base station data result in bias-free and denoised data. 3 main advantages of the natural field method include the depth of investigation always exceeds the capabilities of systems with controlled sources. The method is sensitive not only to conductors, but to resistivity differences in thousands and tens of thousands of ohm meters, which is a challenge for existing time domain systems. And there is no critical dependence on the terrain clearance of the system. This allows for less aggressive flying in rugged terrain conditions, improving the overall safety of data acquisition. The system is operated in the range of frequencies from 26 Hz to 21 kHz, and this range is typically divided into 30 windows. An example of the apparent conductivity curve at a measurement station is provided. During data processing, it is possible to reject data from certain frequency windows, such that only windows with the best quality data and signal are retained. For each measurement station, the output is the apparent conductivity at several different frequencies. Frequency can be used as a proxy for relative depth. Thus, the lowest frequencies provide information about the deepest structures. An example of a map of the apparent conductivity for the lowest frequency, around 26 Hz, is shown here. Apparent conductivity profiles for higher frequencies are displayed on the right with the corresponding resistivity depth image below. To summarize, the results illustrated here are intended to demonstrate the sensitivity of the technology to geologic structures at depth through measurements at the lowest frequencies and to shallow geoelectrical variations at the highest frequencies. For estimation of depth of investigation, the skin depth as calculated for a homogeneous half-space with different resistivities can be useful. Some researchers suggest using the skin depth multiplied by a coefficient of 0.5 to 1.5. For example, if we use 71% of skin depth, as recommended by one of the authors, we can reach 2 km depth at 1000 ohm meter average resistivity. Even in conductive environments, the MT method, which uses naturally occurring EM fields, can obtain a decent depth of investigation, in all cases exceeding the capabilities of airborne systems with controlled sources for primary field. Two examples are provided to demonstrate the impact of conductivity on depth of investigation. On the left is data acquired in a relatively conductive environment, and on the right is data acquired in a resistive environment. The example on the left is data acquired in Central Asia in a region with thick, approximately 400 meter conductive overburden, with resistivity of 100 ohm meters or less. The structure delineated is an orogenic type gold deposit, which can be observed underneath the conductive overburden. In this region, open pit mining is used, but from the point of view of exploration, delineating this deeper geology is important because it is a controlling factor in mineralization. Without the ability to image beneath this conductive overburden, it would not be possible to identify this feature. The second example on the right is data from East Russia, acquired in resistive conditions. Here, the depth of investigation is 2.5 kilometers. The deep domal structure which controls the epithermal gold-silver mineralization is shown. Because the MobileMT system acquires measurements in 3D, the system is sensitive to geoelectrical boundaries in any direction. This example from the Athabasca Basin demonstrates this. The horizontal contact between the sandstones and the basement at approximately 700 meter depth is imaged, in addition to the complex morphologies of the conductors both above and below. If we zoom into the high resistivity sandstone layer, we can see the alteration zone that is imaged in the highest frequencies. This demonstrates the sensitivity of the MobileMT system to highly conductive graphitic rocks and faults in basement, but also to resistivity differences in thousands of ohm meters related to alteration zones in sandstones. This would be extremely difficult to resolve using time domain methods. Looking at resistivity sections from a part of the line shown in the previous slide, a comparison between ground transient audio magnetotelluric data and MobileMT data can be made. In general, the MobileMT data is very comparable with the ground data. This part of the line is over a known uranium deposit. The target's top is between 700 to 800 meters depth at the unconformity contact. A map of apparent conductivity at one frequency from the MobileMT system and a time domain dB/dt map at 220 microseconds are provided side by side. The maps are very similar, even the small discrete near-surface conductor which is visible at the highest MobileMT frequencies. The important takeaway is that these near-surface conductors shield field penetration and limit the depth of investigation of time domain systems. MobileMT shows the full geoelectrical picture including the deep structures. The Huronian metasediments in Sudbury contain many base and precious metal showings. These deposits and occurrences are typically hosted within structural zones with albitization and extensive hydrothermal alteration and brecciation, like iron oxide copper gold style mineralization. This is an example taken from the Aylmer property without good conductors. The time domain system does not show anything except near-surface sediments in the valleys. The MobileMT data reveals deep-seated structures which potentially control mineralization. The magnetic field map shows how the deep conductors are related to magnetic features. The location of the survey line from which the resistivity sections were made is shown over the magnetic field map. The responses in different time gates for a half-space with different resistivity for a time domain system are shown. The induction signal in the thousands of ohm meters range is below the system noise level. This is the reason the time domain method cannot resolve resistivity differences in the thousands of ohm meters. For example, in the previous example where the data were from a comparatively resistive environment. MobileMT does not suffer from this limitation because it is free of noise coming from closely positioned transmitting coils or loops. Here is another line from the Aylmer property near Sudbury. The prospective structure is evident on the resistivity section along the hashed line. A resistivity depth slice at 250 meters below sea level is shown on the left, as well as the magnetic field map on the right. The depth of investigation is at least 1,500 meters. This example from British Columbia is a prospective gold zone. As evidenced by case studies provided here, it is shown that the depth of investigation of the MobileMT system exceeds 1 kilometer, and in some cases is greater than 2 kilometers. From the perspective of mining and production, these deeper structures are not of interest. However, from an exploration point of view, the ability to look deeper is very valuable. From the resistivity depth slice on the left, the structure controlling gold mineralization can be seen mostly at depths of 1 kilometer or greater. On the right is a resistivity depth slice corresponding to 100 meters below sea level and apparent conductivity for a low frequency, with the location of the line overlain. Because of the depth of investigation of the MobileMT system, it is able to resolve deep-seated mineralization controlling structures, which are not detectable at the surface. Most of the examples shown so far have demonstrated the superior performance of the MobileMT system at resolving deep structures when compared with other EM technologies. These sections from Ecuador, Utah, and Tasmania show the sensitivity of the MobileMT data to relatively near-surface resistivity differences, layers, conductors or resistors, along with deeper structures. The output data from a MobileMT survey is apparent conductivity. These data can be inverted to provide resistivity depth models. 3 types of inversion are used on MobileMT data in practice. The first is nonlinear least squares inversion based on the conjugate gradient algorithm. The results of this are presented as sections, 3D resistivity voxels, and depth slices. The second inversion approach is 2D inversion based on the MAR-E 2D-EM algorithm. Today, it is one of the most advanced tools for 2D inversion of magnetotelluric data. Similar to the case of 1D inversions, the results are presented in the form of sections, depth slices, and 3D resistivity voxels. Expert Geophysics works together with organizations who in turn collaborate with universities that provide 3D inversions of MobileMT data. For deep structural mapping, Expert Geophysics conducts lineament analysis on a series of resistivity depth slices and joins the results into a 3D view. The example provided here shows the results of structural analysis up to 1 kilometer depth over the basement of the Athabasca Basin. As opposed to other EM systems that use controlled primary field sources, terrain clearance is not a critical parameter that impacts the quality of MobileMT output apparent conductivity. In general, during survey flying, the aim is to keep the system around 60 meters above the ground. In rugged terrain, this is often not possible, and the receiver height can sometimes exceed 300 meters. But these differences in flying height are not reflected in the MobileMT data. This is a significant advantage of the MobileMT system over other controlled source EM systems, especially for data acquisition in rugged terrain. This is an example of a survey flown over an active mine site. Regardless of the influence of industrial power lines, the ore deposit controlling structure is recovered from the MobileMT data. The similar dome-like structure to the east of the known deposit is a potential for new discoveries. MobileMTM is a modified version of the MobileMT system, which focuses on resolution at higher frequencies by employing more narrow frequency gates than the original system. Unlike the original MobileMT system, which records measurements from 26 Hz to 21 kHz, the modified version records measurements at frequencies from 90 Hz to 27 kHz. The system also measures the horizontal gradient of the magnetic field using two cesium vapor magnetometers. Airborne magnetic and electromagnetic surveys have been used extensively for kimberlite exploration because kimberlites have distinctive magnetic and electromagnetic signatures. They generally produced roughly circular anomalies. While the magnetic susceptibility of kimberlites is typically high, it varies, and there are known kimberlites that don't have a clear magnetic signature. Yet, they exhibit electromagnetic responses due to contrast with surrounding host rocks. Often, the near-surface weathered kimberlite portion and overlying volcanic sediments exhibit higher conductivity that can be detected by airborne EM systems. Significant pipe anomalies are characterized by significant conductivity appearing at depth. The KL01 and KL22 kimberlites were discovered in Klock and Van Nostrand townships in 2004 by Contact Diamond Corp. Using a combination of till sampling and geophysical methods. The kimberlites are hosted in Proterozoic sediments that are made up of siltstones, argillites, sandstones, and conglomerates. Both kimberlites form positive magnetic anomalies. Two MobileMTM test blocks were planned, one over KL01 and the other over KL22. The blocks spanned an area of 3.25 kilometers squared, and the lines were planned approximately 55 degrees east of north at a line spacing of 100 meters. The data from the KL01 test block show the location of the kimberlite as a high in the apparent conductivity grid at 8,550 Hz. This is corroborated by a contour extracted from the magnetic data. Looking at the apparent conductivity profiles along a single line, the kimberlite anomaly is subtle at lower frequencies and becomes more pronounced at higher frequencies. The pipe structure of the kimberlite is observable in the inverted resistivity depth slice. With superior resolution capabilities at higher frequencies, the MobileMTM system is particularly well suited to delineate such anomalies. As was the case with the KL01 data, the KL22 data show the location of a kimberlite as a high in the apparent conductivity grid, and also as a magnetic high based on the overlain contours. Apparent conductivity profiles show the same trend we saw for the KL01 block, in which the anomaly becomes more pronounced at higher frequencies and the pipe-like structure is apparent in the resistivity depth section. As of October 2021, Expert Geophysics has flown over 50,000 line kilometers of MobileMT commercial surveys in 9 countries, including Australia, Canada, Ecuador, Peru, Colombia, Kyrgyzstan, Kazakhstan, Russia, and the United States. Several of these surveys were performed in rugged terrain. MobileMT surveys have been completed for applications and exploration programs for porphyries, orogenic gold, epithermal gold-silver, and sub-epithermal gold, IOGC type VMS, uranium, nickel-copper sulfides, and kimberlites. In conclusion, the MobileMT technology based on natural EM fields has several advantages over other airborne EM systems, including greater depth of investigation, spanning both near-surface and deep structures. The system is sensitive to resistivity differentiations in the low and high resistivity ranges, including thousands of ohm meters. It is sensitive to geoelectrical boundaries in any direction, and it's safe to use in rugged terrain conditions. Thank you very much for your attention.